focused? Okay.
So now, you don't have to have this right now, but do you guys remember this handout from a while back? Even if you don't, this is a handout from a while back in this class. This was for an NPQ problem where it was 50%, and I did something for 14 times, right? Would you say that this distribution looks decently normal?
Yeah.
Yes, and remember, we actually calculated the mean. The mean was just 14 times 0.5. The mean was 7. And see how the 7 is the highest bar. And it's got room. I want you to really kind of get the idea of this. It's such a beautiful idea. It's got room to go up and come back down. What the shit do I mean by that? Well, what if the mean would have been instead, if the mean would have been, I need paper. Sure, I'll use this. If the mean would have been instead, like 1, let's say the mean was 1, then the highest bar should be right at 1. Would you say that's normal? Does that look normal?
Yeah.
It doesn't have enough room to go up and come back down. The mean has to be big enough so that it's got room to go up and come back down. Now, if I make the mean too big, like here, what's the largest the mean could be would be 14, because that's the most. I only did it 14 times, right? So what if the mean would have been 14? Then this would have been the highest bar, and it would have went down from there. Does that look normal? No, so then I need this side to be far enough away. I can't have the mean be so close to either wall, because then it doesn't have room to go up and come back down. So NP hat is the one that brings it out from here, because that's the actual mean. That's the average number of successes. NQ hat is the one that brings it out from there. So that becomes, if NP hat and NQ hat are at least 5, if those are at least 5, then that means it's far enough away from the wall so that it has room to go up and come back down and look normal enough. And here, what was the mean? It was 7. NP was 7. NQ is also 7. They're bigger than or equal to 5, therefore this is officially normal enough. I could have used z-scores on this stuff, because it's normal enough. So here, is that true for this problem? What's What's NP hat? What's NP hat? N is 652. P hat was 0.704. I'm hoping somebody out there is like, why the hell is he doing all that work? Maybe not yet, okay? I'll bet you anything it's 459, something close to that. Because how do you figure out P hat? To figure out P hat, don't you do X divided by N? The number of successes divided by N. So what is NP hat always going to be? The number of freaking successes, right? There's a little shortcut for you. Remember that problem I did a minute ago? What's NP hat here? Who gives a shit about N is? NP hat is 13. Is that what I get P hat? 13 out of 80. And what's that times 80? 13. The 80s cancel. If you don't understand what I just said, just plug N in and P hat in, multiply them, make sure it's at least 5. All right? But some of you guys, I'm trying to show you, there's a little shortcut there because of the beautiful algebra cancellation stuff. So this now is the check for an NPQ problem to be normal enough. NQ is going to be the rest. NQ would be 193, I think. Yes. Because 193 are failures. So they're both bigger than or equal to 5. Check. So that means it's normal enough. That's why we're allowed to do all this stuff. It was normal enough. Now, the last thing that we do with these, what did we do? The very last thing last time was we figured out if I want the error to be smaller, how do I figure out how large my sample has to get? To make my error smaller but keep the confidence the same, something's got to change. And what always improves our confidence in what we see in a sample is to make it larger. Make N bigger. So if we do all the stuff we did last time, we start here and we just solve for N, multiply by square root of N, divide by E, and then square both sides, and I get this. what we did last time, basically, except we didn't have a square root in there. Well, we did, but not over everything. That is going to be my formula for if they ask how many do you need to be within whatever. So in this part A, what is the error that I want? What error do I want in part A? Yeah, 3%. I want my error to be 3%, 0.03. What was the error for a sample of size 652? What was the error? 0.366. Almost 4%, just a little bit over 3%. So my sample size should be bigger than 652 here. Does that make sense? To have a smaller error, my sample has to get bigger than it was, so that I'm more sure about what I see. At least let that make sense. Okay, so now, here's the real key to this, though. What does this not tell me that I need for the formula? What do I need for the formula to work? I need a z. So 99% confidence, we did that a minute ago, was 2575. I'll remind you guys of that. So the z-score is 2575. The error is 0.03. Do I have p hat and q hat? Nope, I don't. And be really careful. Do not confuse that with anything. That's the error. That's all it is. What is your, like right now, the classroom next to us, what percentage of the people in that classroom are men? You don't know. So what's your best guess? 50%. It's my best guess. That's the way to kind of cut your losses, because if there's something you completely don't know, what percentage of astronauts like to wear shoes that don't have shoelaces? Hey, no freaking way in hell. So what's the way to cut your losses so you're as close as you can be to any possible answer is? Half of them. Right? If you go one way, then you could guess wrong. So 50% kind of gets you the closest you could possibly be without knowing shit. Now, mathematically, so in general, if I don't know p hat and q hat, what am I going to guess they are? 50-50. I'm going to guess p 0.5 and 0.5. Why? How should I be punished, statistically speaking, if I don't know something? Shouldn't the result be the worst thing for me? So in this case, n represents what? What would n represent in this case? What does n represent here for this problem? What does n represent? The number of, keep going, number of, number of students I need to talk to, right? Do I want n to be really big? No. So if there's something I don't know, statistics will not punish you, but you have to be more conservative. So 0.5, putting 0.5 in for p hat and q hat makes n the largest it can be. Anything else for p hat and q hat makes n smaller than it would have been if I would have put 0.5 and 0.5 in there. So it makes sense on two fronts. I don't have a freaking clue, so I'm going to guess 50%. But also, mathematically, it makes n bigger than it could ever be. That's kind of like your punishment for not knowing something. So here, I've got to guess 0.5 and 0.5. So now I've got everything I need for the formula. N equals 2.575 squared times 0.5 times 0.5 divided by E. The biggest mistake there is people forget to make it into a decimal. A percentage is something that we completely made up, right? The decimal is the actual number. So my prediction for this was it was going to be bigger than 652 because that size of a sample got me just below 4% error. Now I want to go all the way down to 3% error. I'm going to have to talk to more people. So see what do we get when we do this. What do you guys get? Some of you guys like, I'm waiting people. It's not faster. Anybody think they have it? 1841? Point. It doesn't matter really. You always round this up. Anything less than this will give you more error. So to make sure that you're less than the area you want, you always round up. So I'm going to have 1,842 people. How many people did I already talk to? Oh, this is a totally different problem. In general, I could give you a question where you've already done some work, and then I say, how many more people would you have to talk to? I'm not going to take points off if you don't subtract here, but if I'd already, like on this next part, it says, if we had done a preliminary study of 42 stat students and found 31 of them passed the first time around, now what can I calculate that I had to guess at before? We talked to 42 people, and 31 of them passed stats the first time around. What can I calculate from that? P hat. P hat would be 31 out of 42. That makes Q hat equal to 0.262. So earlier we had to guess it was 50-50 because we had no idea. The problem didn't tell me. Now they're saying I did a preliminary study and I found this. This is one reason why preliminary studies are done, is to set up some baseline from which you calculate things better for the next step. So now I can plug out everything in there. I get 2.575 squared times my P hat, Q hat that I now have. And this is going to be much less than 1,842. Let me sail the ocean blue. I like the idea of that. Not a huge amount less, but I mean a decent amount less. I get 1424 point, who cares, 1425. It's over 400 people less that I have to talk to.
Am I late or are you early? Or?
You're early. Is that the right time? Yeah. Sure, you're here already. Go ahead.
I didn't realize I was breaking into your class. Oh,
All right. Let me give you guys one to try on your own. Okay. All right, we checked 54 tires, and we find 9 of them overinflated. Find let's make it 90% confidence interval for the true percentage of tires that are overinflated. Be sure to check to make sure it's normal first. Check to make sure it's normal.